Hello, and welcome back to my YouTube channel. My name is Professor Govalla, and today we're going to be doing two source transformation examples, specifically this one and this one. And if you would like to pause the video and see if you can try these on your own, and then come back to the video and see if you got the right answer. Before we dive into these examples, though, I would like to formally define what source transformation is and why it is necessary in circuit analysis. For the formal definition, we say that a source transformation is the process of replacing a voltage source Vs in series with a resistor R by a current source Is in parallel with the resistor R, or vice versa. Again, this Is, this S here, is simply source. Why do we need source transformation? We say that it can reduce a complex circuit into a simpler, more solvable form, especially when using things like nodal analysis or mesh analysis. It's also very flexible for different methods. For example, if you wanted to use mesh analysis, maybe you consider mesh analysis to be an easier analysis method for you. You can convert your complex circuit using source transformation and then go ahead and use mesh analysis on a simpler, less complex circuit. The same thing goes for nodal analysis. If you have a complex circuit and you want to reduce it or make it less complex and then further use nodal analysis, you can do that. The third benefit to source transformation is it allows us to combine sources. So for example, if you have voltage sources in series, you can combine them by adding them up into one bigger source. As well as if you have current sources in parallel, you can combine them by adding them up like this. Now let's go ahead and talk about what I'm going to mention as the goal of source transformation. And again, the goal is simply, we want that if you have a circuit connected to a terminal AB where there's a resistance R and a voltage source, we want to be able to map it to a current source in parallel with that same resistor R. All right, and it's also connected to A and B. As a simpler way of saying this, I want that if you give me Vs and R, I want to map this to an Is and R. And if you give me Is and an R, I want to map it, to a Vs and an R. And the way we do this simply is by looking at the Thevenin resistance and the Thevenin voltage and the Norton current of these circuits. So let's start off with the Thevenin resistance. I'm going to go ahead and delete this. And I'm going to say that R Thevenin is equals to V out over I out when my Vs is equals to 0. This is also equals to V out over I out when my Is is equals to 0. All right. So in this case, in case 1, we call this case 1, I'm going to short circuit Vs because it says my voltage Vs is 0. And I'm going to take an ohm meter and probe it right here. And I'm going to see that the resistance between A and B, R Thevenin, is simply R. And for Is, for Is to equal to 0, this means it's an open circuit, right? Because current cannot flow through an infinite resistance or open air. So it's going to be an open circuit. I'm going to take my probe again. I'm going to say, what is my resistance between A and B? That's R Thevenin, which is simply equals to R. So as you can see, the R Thevenin of both my circuits is simply just R. And if this is new to you, I do have a Thevenin equivalence and a Norton equivalence video in this playlist. So please feel free to check that out. Okay, so the next step to finding Thevenin equivalence is finding, we could do either a Thevenin voltage or a Norton current. So I'm going to do both as a refresher. So I'm going to find V Thevenin. So if I have a circuit like such, VS R A B, and I'm asked, what is my voltage here, V Thevenin, right? You can easily see that this is simply equals to VS. Or if you can't see that, imagine that this is A, this is RL, this is B, and this is VS, where RL is infinity, and this is R. So the voltage drop V Thevenin across this AB is going to be RL over RL plus RS times VS, which is simply infinity over infinity times VS. Infinity over infinity cancel out, so V Thevenin is simply equals to VS. So that's how you can prove that really quickly. But again, the drop across A and B, if you put a voltmeter across that, is VS. Okay, so now we say that the goal of this source transformation is to have this circuit here to be equivalent to this circuit here. So RL. So that means that our V Thevenin, we need to find V Thevenin, VTH. But VTH, as you can see, is simply, because my IS flows through here and goes through here, so it's going to be simply VTH is equals to IS times RL. But we know that VTH is equals to VS, which is equals to IS times RL. Or we could say that then IS is equals to VS over RL. So this means that, okay, if you give me circuit 1 located here, and I want to convert it to circuit 2 located here, I'm going to divide my VS by RL. I'm going to do VS divided by RL, and I'm going to put that RL in parallel, or just R, actually. This should just be R. I'm just going to put that R in parallel with IS. So I hope this makes sense in terms of how we can convert it. And obviously, if you're given IS and in parallel with R, you can simply just multiply R by IS to get your VS and put it in series. And you can go back to circuit 1. All right. So let's do the Norton method just as a refresher as well. So we want to do this by finding what's called Norton. All right. So we start off having our circuit, a voltage source in series with a resistor R. This is VS. And Norton says we're going to connect a wire. We're going to short this. We call this I short circuit. The same thing as Norton, right? And what we can do is we can write a simple equation, right? So we could say minus VS plus R times I, let me call it I short circuit. It's equals to 0. So then simply put I short circuit is equals to VS over R, which is equals to IN. Next, we can talk about, we want to map this for equivalency to a circuit IS in parallel with RS This is A. This is B. So what we're going to do the same thing. We're going to short it. This is called I short circuit, or again, we can call this I Norton. And we notice that my current IS is not going to go through this resistor R, right? Because it has a resistance. It wants to go through the path of least resistance. So it's going to go through here. So essentially, we can say then that I short circuit is equals to IS, or I source, which again is also equals to I Norton, which from this equation here is equals to VS over R. Or simply put, IS is equals to VS over R, or VS is equals to IS times R. And again, similar to the previous voltage Thevenin that we proved earlier, if you're given a voltage source in series with a resistance, all you have to do is divide that voltage source by a resistor and put that resistor in parallel with my current source, right? And similarly, if you're given a current source in parallel with a resistor, you multiply the two and you get your voltage source, and then you put that resistor in series with that voltage source. So I hope this makes sense in terms of how we prove and we apply source transformation before we dive into examples in this lecture and also in further lectures. If you have any questions, please leave them down in the comment section below, and I'll be sure to get to you. So let's go ahead and do this first example. And as we notice here, we can do this many ways, right? We can do nodal analysis. We notice that there might be a super mesh right here, right? So that might complicate some analysis. Even nodal analysis, there's two unknowns, so that might complicate things. So let's go ahead and simplify this circuit using what we just learned, source transformation. And I'm going to do this in 3 steps, right? So I'm going to say step 1. And again, the goal here is to find this VO right here, the voltage at the 8 ohm resistor. So step 1, I'm going to combine, or I'm going to transform, let's say this part here, and I'm going to transform this part right here. And let me zoom out a little bit so I get some more room. And what it looks like is simply, since this current source is going down, it's going to be minus plus. This is grounded. I'm going to connect this in series with a 4 ohm resistor. This is going to be that 2 ohm, 8 ohm. And this is 3 ohm is going to be in parallel with a current source. Again, the current source is going to be 12 divided by 3, which is going to be 4 amps. And over here, we're going to get 3 times 4, which is going to be 12 volts. So I hope this makes sense in terms of how this transformation was done. So let's go ahead and do the step number 2. I'm going to do it up here. And I'm going to say that I want to transform this voltage source in series with these 2 resistors. And essentially how that looks like is a current source in parallel with a 6 ohm resistor, because 4 plus 2 is 6. This is going to be 12 divided by 4 plus 2, which is simply 2 amps. We can then talk about my 8 ohm resistor. My voltage drop is VO here. And then I'm going to keep the 3 ohm resistor and the 4 amps current source. All right. So then we can then finally do another transformation here. So we call this step 3. I'm actually just zoom in. We could call this step 3. And what this looks like is simply, I'm going to combine, it's going to be a little bit weird. I'm going to combine this with this, and along with this and this. All right. So this is what it's going to look like. It's going to be a 8 ohm resistor in combination with a 6 ohm resistor in parallel with a 3 ohm. And then remember how I said current sources in parallel can be combined. So it's going to actually go up because 4 is greater than 2. So this is going to be 4 minus 2 since they oppose each other, which is going to be 2 amps. And this is going to be plus minus VO. This here is 6 times 3 divided by 6 plus 3, which is going to be 18 over 9, which is going to be 2 ohms. So you have a 2 ohm resistor in parallel with this 8 ohm resistor. You have a 2 amp current source. We can go ahead and do current division, right? So I'm going to say I 8 ohm is simply 2, which is the current or the resistor that we're not trying to find the current through. It goes on the numerator, divided by that resistor plus the resistor that we are trying to find the current through. Then we multiply by our current source. Again, I've talked about current division in the past, so please make sure to check out my previous lectures or videos to understand it well. So then this becomes 4 over 10, which is 0.4 amps. And essentially, VO is 8 times I, 8 ohms, which is going to be 8 times 0.4, which is equals to 3.2. Now, note how simple this was, right? I did this in 3 steps, and I didn't really do any math, like, systems and equations, things like that. I simply only did a voltage division, but it was very, very simple, right? And a lot of times you can even do this by inspection. So that's the real benefit of source transformation. Another alternate method, as if you can see here, is that an alt method you can see is that the voltage drop VO through here is the same as the voltage drop through here. So what we can do is we can say that VO is actually equals to 8 ohms in parallel with 2 ohms times my 2 amp source. So this is going to be 8 times 2 over 8 plus 2 times 2, which is equals to 32 over 10, or 3.2. So that's another method of doing this without doing current division, right? Okay, let's go on to the second problem now. So this is the second problem. Again, based on the first problem, if you want to pause the video and see if you can try this one and see if you can get the solution. But I'll go ahead and walk through it now. But first, we want to notice some things, right? We want to notice that we have a super mesh here, again, and a super node right here. Again, I've done videos on super mesh and super nodes, so please feel free to check those out. But the problem's asking us to find IO through this 7 ohm resistor. And we don't want to do all the complex analysis like nodal analysis and mesh analysis. We want to simplify this circuit. And I'm going to do this again in 3 steps, right? So the first step is I'm going to simplify this current source in parallel with those 2 resistors, and this current source here in parallel with this resistor. And I'm going to say then that, so my step 1 simply is going to be this voltage source with a resistor. I made a mistake here. I'm actually going to combine the 6 ohm, the 3 ohm, and the 5 amp. All right. So this is going to be minus plus. Let me just draw all my components for this step. and then I'll explain. So essentially, this here becomes 3 in parallel with 6, or again, this is 3 times 6 over 3 plus 6, which is 18 over 9, or simply 2 ohms. This here is 5 times 2, right? Because it's a current source and a resistor in parallel. So I multiply my 5 amps times my 2, which is equals to 10 volts. This 5 volts source stays. This is 7 ohms. This current source is replaced by a voltage source. So 3 times 4 plus 1 is 5. So 3 times 5, which is equals to 15 volts. And again, this here is 5. This here is 5 ohms. All right. So let's go ahead and do step 2. And simply, step 2 is going to be simple. I'm just going to combine these two. All right. So step 2 is going to just be plus minus. So this is going to be 10 plus 5, which is 15 volts. So 2 ohms, 7 ohms, 5 ohms, and 15 volts. Again, this is the current I'm trying to find, IO. Okay. So again, as you can see, step 2 wasn't that complicated. But here we go with step 3 now. So step 3, I'm actually going to rearrange this back into current sources. And again, using some analysis, you can find IO from this point using like nodal analysis or mesh analysis. But since this is a source transformation video, let me go ahead and do another source transformation so I can really bring home the point. So you have this current source, which again is going to be 15 divided by 2, or 7.5 amps. You're going to put it in parallel with a 2 ohm resistor. I'm going to leave my 7 ohm resistor as put. This is going to be in parallel, so 5 ohm resistor in parallel with another current source, which is going to be 15 divided by 5, which is going to be 3 amps. All right, and I'm trying to find this IO. Okay, so this makes it very simple, right? I'm again going to use current division. And again, remember, current division says IO is equals to the numerator is the resistors that IO is not flowing through. So this is going to be 2 in parallel with 5 over the resistor that it is flowing through plus the resistor that it's not flowing through. So 2 parallel with 5. And obviously, I'm going to combine, since my current sources are in parallel, I'm going to combine 3 plus 7.5. Just to be explicit, 2 in parallel with 5 is simply 2 times 5 over 2 plus 5, or 10 over 7, which is around 1.42. So then we say that IO is around 1.42 over 7 plus 1.42 times 10.5, which is approximately 1.78 amps. So this is your IO answer. If you got these problems correctly, good job. If not, if you're confused, please leave down a comment, and I'll be sure to get back to you. Now, I would like to point out that I did use a lot of steps to explicitly show source transformation, but even with these steps, you can see how it's easier to analyze compared to doing things like supernode, mesh analysis, super mesh analysis, and node analysis. If you like the video, please give it a thumbs up. And please share my videos and subscribe to my YouTube channel. Thank you.